Paleoseismology is the study of past earthquakes as they're preserved in the geologic record. So I'm a paleoseismologist, and the types of features that I study are earthquake-induced liquefaction features and tsunami deposits. I've also looked at active faults, but mostly these days I'm working on paleoliquefaction features. Earthquakes, especially the larger earthquakes, those that are greater than magnitude 5, can induce what's called liquefaction of sand layers at depth. So if there's an earthquake of magnitude 5 or greater and there are sands below the surface that are saturated with water, if they're shaken strong enough and large enough, they can liquefy, and that liquefied sand and water are brought to the surface and they form what are called sand blows. So what's involved in studying liquefaction features often begins in the office with reviewing geologic maps of the area, getting an idea of the age of the deposits and perhaps their susceptibility to liquefaction. And in addition to that, we would look at aerial photographs or satellite images to look for a signature of light-colored patches in places where you wouldn't expect them, such as floodplains, which are often covered with flood deposits, overbank deposits of silty and clay material. So they tend to be dark. But sand blows, which is sand brought up from below and deposited on the floodplains, form these light-colored elliptical patches. So when we go to the field, we might go to these areas where we've identified likely sand blows from reviewing aerial photographs and satellites and verify that interpretation by digging soil pits, excavating trenches, and if we find that in fact they are, and one of the key criteria for determining that is if there is a vent, a sand dike, a fissure through which the sand had vented to the surface, then we would study that feature in detail. But we would also want to go to places that you might expect features to form and see if you can find anything or not, because you want to be able to delineate the limit of liquefaction. As the area over which you find the features tells you something about where the earthquake was located and also the magnitude of the earthquake that formed those features. So the information that we've learned about past earthquakes gives us a better idea of what to expect in the future. Now, we can't really predict when earthquakes will occur, but we have an idea of the way the fault systems in the area behave, how often they produce earthquakes, how large the earthquakes are, what sort of levels of ground shaking we might expect. It's unlikely that a new Madrid earthquake sequence will occur in the next 50 years, a low probability. So it's a low probability event, but it would be a high impact event if it occurred. In addition, there are lower magnitude events, 6s, which have a higher probability of happening. So we should certainly be preparing for those and thinking in terms of our priorities about these big impact events. What should we do just in case we had a really big earthquake?